So welcome all of you to my presentation of my thesis I've been working on for the past few months. So we'll just start right away. So creating 3D models of our environment has seen much a rapid increase in the interest in development and research over the last few years, such as the mining industry, the forest industry, the car industry, the defense, and so forth. And a common one method of doing these 3D models is known as light detection and ranging, or LIDAR for short. And as the name suggests, it uses light to do this. And a very common instrument employed in this is a laser scanner. And note that it's a laser scanner, not a laser. A laser just shoots out a beam of light. So this scans it as well. And I will also point out that the 3D models that we talk about in these cases, like for the laser scanner, are usually referred to as point clouds. So this is what I will use to refer to these 3D models of our world. It's a point cloud. It looks like a cloud of points, like in the picture here. It's a bit hard to see actually, but you get the point. So there are sort of two categories of laser scanning. It's airborne laser scanning, which is done by air, of course, and there's also ground-based, known as terrestrial laser scanning. And this can sort of be subcategorized into either being static or mobile. And I will go into more detail about these two cases, just talk a little bit more about them. I won't cover any airborne. I will just mention that it exists. Okay, so static TLS is commonly just referred to as TLS. So you don't say static TLS. You usually just refer to as TLS, and you know it's the static case. I don't know why, but that is what I will also use. So if I say TLS, it means the static case. And one of the great advantages with TLS is that it's very accurate. And by that I mean you can get very good models of the reality. Or you can get very good point clouds. Okay? But the problem is that it's quite cumbersome and requires a lot of work in some cases. So let's say you want to move, you see this in the pictures there, it's used in a range of different applications. Like in a cave here, and a forest, and the pyramids. But you see that the kind of standard stuff you use is like this tripod, and then you have a big, heavy laser scanner on top. So if you say you want to move this around, you're going to have to move all this stuff around, and it's quite heavy and time demanding. So then there's mobile TLS, or mobile terrestrial, or mobile laser scanning, I mean, or MLS for short. So then you just put your laser scanner on something mobile, maybe a car or a person, which in this case is me in that picture. Well, it's actually a backpack on me. Or a robot, whatever it is you want to use. But in these cases, you usually want to do something called dereference, and by that I mean that you want to sort of put your model, your point cloud, in a world coordinate system, like latitude, longitude, and altitude. You don't want it in local coordinates. So you want to know where you took your point cloud data. So well, then you think, well, maybe we can just use a GPS, or the more general term, a GNSS, which stands for Global Navigation Satellite System. So we can just use that, and well, then we know our positions, and we can carry that with us during, say, when we're scanning something. But, as I think all of you know, this does not work well when you're, say, inside, or let's say in a forest. Then this will work quite badly. So, for example, if you take in forest then you have something called multipathing, which is when the signal between your satellite, or between the satellite and your receiver, it will bounce or reflect on nearby objects that reach higher than your receiver. So in forest, it will reflect on trees and on maybe even the canopy, or maybe you have a big canyon wall or something. So this is not limited to forest either. It's you can have buildings as well. But in forest you also have absorption. So the tree canopy can absorb your signal, so you don't get a signal at all. And even the stems can absorb your signal and block it from reaching your receiver. So just using a GNSS in forest is very troublesome when you want to know your position. You will get very varying quality in your position estimate. And I also should mention that positioning for the MLS case is much harder than for TLS. Okay, so what do you do then? Well, you include other measurement instruments that can measure your position by other means. And the most common one are GNSS, a laser scanner, and something called inertial navigation system, or INS, cameras, and some other stuff you can also use that I will not mention. But all of these instruments have their downfall, their ups and downs, so to say. And for example, the inertial navigation system, which is very, very commonly used in like airplanes, aircrafts, I mean, is that they suffer from accumulation of error, or drift, as it's called. And that comes from, well, the INS it's composed of gyroscopes and accelerometers. So it measures accelerations. And to get position from that, you have to integrate twice. And this induces an accumulation of error over time, which gets worse and worse. But the idea is, if you combine instruments like a GNSS and a INS, is that you can sort of make them support each other, so that when one instrument struggles, another instrument can sort of be given more weight and can take over, and vice versa. And this is usually referred to as sensor fusion. And it can be done either after you take measurements, in post-processing, or real time. So my focus on this, in this thesis, has been assembling a backpack-based MLS system to be used in forests, composed of GNSS, an INS, and a laser scanner. And the questions I wanted to answer was, how does the MLS system compare to TLS and manual caliper measurements, and also compare to other studies as well. But how does it compare mainly to TLS and caliper measurements? And then post-process the data with the dynamic calibration algorithm, which I will cover a bit more later on. And then my question is, can I expand this and improve this? Does this algorithm work with my system? And if it does, can I improve it? And the MLS data was then, well, as I said, it was compared to TLS and manual caliper, mainly using or looking at the diameter at breast height, which is the diameter of the trees at the breast height, roughly 1.3 meters above ground. Or DBH, using root mean square errors, RMSE, and bias mainly. And just for reference, this is how RMSE is defined. It's not very intuitive, actually to see exactly what it means, but let's just see it as an error, a measure of error. And then the bias. So I talked about georeferencing and the issue of positioning in forests. But what are the effects of when you actually georeference to this coordinate system that has a very varying quality of the estimate? Well, you will see that you will have multiple tree copies and multiple ground layers. And to illustrate this, let's say I'm scanning, I'm walking with that stuff, and I'm seeing this tree at time t1. And I'm walking, and then I'm coming back to maybe roughly the same position, and I see this tree again. The laser scanner sees this tree again, and the ground as well, at a later time, t2. Well, since we have another error at this time, we will have that the tree is actually, well, we will see two trees, duplicates of each other, located at different locations in space due to this error. And the dynamic calibration algorithm aims to try to solve this and also to sort of correct it to reduce other errors. But it's actually part of, it's just the algorithm itself is actually sort of a small part in a series of tools or graphical user interfaces written in MATLAB. And it was developed by Mikael Tulldal and some other guys at FOI. So basically what it does, it uses previous data, so data we have seen before, it uses that to adjust your point cloud and hopefully correct for multiples and other errors. So the system I used, well, names are not very interesting, but you see it here. This is a receiver, and this is the laser scanner, and down here is an INS. And then the rest is just other stuff. So what did I do to the dynamic calibration algorithm? Well, first of all, I adapted it, so it had to work with my system. And then I expanded it. The main expansion I did some other expansions as well, but don't have time to talk about them that much. But the main one is a vertical point cloud correction. So I said that the trees were located in different locations in space due to drift and so on. And previously it corrected in the horizontal direction, so duplicates were corrected horizontally but not vertically. So they were still located at different heights. So I fixed that, and I also tested and bug fixed it quite a lot. They had not tested it that much. But the survey was done at Stadsliden at the end of March. Roughly 12 minutes of survey time, a bit less in the forest. But the area of interest, it's very hard to see, but it's an area down here. That is the area of interest here. It's roughly 40 meters in diameter. This is where the results were taken and analyzed. And the TLS data set that I compared the MLS with was for the same size, but the caliper data was smaller. It was roughly 24 meter diameter within this area. And that's me on the backpack with the backpack. So there was a lot of post-processing, bug fixing and stuff. We'll reach the results in this case. And here we see the top two figures are before we have adjusted, before we have calibrated, post-processed. So we see here the color represents when we saw the trees. So blue is we saw it earlier, and yellow is we saw it later, and green is in the middle. Okay. So here we see that there's a lot of multiples. And we see that there's also a lot of drift. The yellow trees here are very elongated. But there's a lot of multiples here. And then after we post-process, we see that they are adjusted to the same position. We see that they have been adjusted vertically as well. So the vertical translation works. And we can also see this. This is, I also mentioned, this is for just a small region. So this is just your trees. It's in a small region. But this is for roughly the entire area inside the forest. So we see that this represents the ground layer. And we see that from the side we have a separation where the ground should be the same height, so to say. If we had zero error, this would be located at the same heights. But after we calibrate, we see that they have been adjusted to roughly the same heights. Okay. So to compare this also to TLS and caliper, I first had to do something called co-registration. And this basically means that you match the data sets together. So the same stuff, the same trees in the MLS correspond to the same trees in the TLS, for example. But anyway, in doing so, we can start comparing tree properties and such between the data sets. So the DBH RMSE and the DBH bias is what I'm showing here, and you can read the numbers. But if we do this also for the TLS and caliper measurements, we see these values, and well, roughly it's smallest, middle, and then the largest values here, except for these two. But we also compare this to other forest studies. We see that one study, TLS study by Johan Holmgren here and Kenneth Olofsson, they did a TLS study in forests where they compared TLS to caliper, and they obtained these DBH, RMSE, and bias. And we see that these actually correspond very nicely to these for diabet. So that's nice. But furthermore, we also compare this to a backpack MLS study done by some Finnish guys, where they compared MLS to TLS. And they obtained slightly higher values than I. But, so these values are good, but every measurement instrument has its errors. So it's a bit hard actually to say this instrument is worse. But everything has its errors. Certainly TLS and caliper has their errors. But ideally we would like that all these comparisons, these values would sort of converge to each other and wouldn't have much difference between them. But we see that the MLS compared to TLS and caliper is not very far from, let's say, TLS and caliper. So this it's good values, but it's hard to say. There's no limit to say that we want an RMSE below, I don't know, 5 centimeters. But anyway, they are good values to summarize. And some conclusions. Well, a backpack system, MLS system, was put together, assembled, and analyzed. And there's a lot of potential to use this in the future based on these results. And future work would include more forest tests, for example, in varying forest properties like tree density and, I don't know, tree types. Maybe a very dense forest where you can't see anything, or very sparse forest. And maybe try different walking patterns to see how that affects. And this will also mean that you have to expand the dynamic calibration further if you want to use this, of course, to make it more general. So there's a lot of room for improvements, and also improvement to just the hardware to do that as well. And maybe this could lead to creating I don't know, autonomous harvesters that go out and trash the wood themselves. Or maybe just serve as some sort of tool to help the driver. Maybe it's like a screen where he can see, oh, this tree, cut that tree, and he just presses a button and it cuts the tree. And even if it doesn't maybe revolutionize forest industry, maybe it's just a small industry in the future, it could, the technology is very applicable in other areas such as self-driving cars and robotics in general. So there's a lot of applications for just the technology itself, which is not just limited to these uses. And yeah, this is a summary. I don't know what's the time. Anyone has time?
You have 10 minutes. More or less, more.
Oh, I'm quick. Well, the summary here. Successful translation, good RMSE and bias, much potential to use this in the future, and future work. But to finish, I just want to show you some pictures. I did a walk through Naturvetarhuset here at Umeå, and then I took some LIDAR, some laser data from that. Just to show you some pictures. I think they will look quite bad on the screen, but I will show them anyway, which I think are pretty cool. So this is from, oh damn, this is really hard to see. Well, this is the main building. Most of you know it, and the glass facade that you see when you come from the outside. It's much easier here. And this is from the outside, a top view. So this here you see the side of the buildings, and you see all the windows, and you see there's some trees. And I don't know, maybe you can see it here. Do you see this line here? So this is the line, this represents where the INS was. So you can actually see it wiggling like this when I'm walking. So it's going up and down like this. So here the building is Naturhuset. And I walk like this, blah blah blah. And this is just another view. Here's an entrance, another tree, and you see the little small flower fields. And then, yeah, this is the inside of the building. So you see here's some pillars. Here's the third floor of the building, and the second is here. And you see here, you see the stairs are here. It's very hard to see, but I guess you see a rough view of it. And here we see also the trajectory. But another view, looking down from the stairs on the third floor, you see all the pillars here and the railing here. And this I think is pretty cool. You see, this is between the Naturhuset and the physics building. So here's a bike, you can see, and you can see there's a small sign here which says 41. And then you see this thing here. That's actually some guy on a bike, and he's, I don't know where he's cycling. But here you see there's a tree here, and here's the physics building, and then we have a part view of the skywalk between the buildings. Here we see from another direction, here's the guy again, the trash place. And yeah, thank you all for listening.